All right, we are right at the start time, 2 o'clock Eastern Standard Time, so we'll go ahead and begin. First off, good afternoon. I'm Jason Thomas. I'm a project engineer at America Makes and your host for today's America Makes TRX webinar series. A little background on the TRX webinar series before I introduce our speaker. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium called the America Makes Technical Review and Exchange webinar series was created. By creating this platform, it allows the additive manufacturing and 3D printing community to come together and share knowledge and experience with a broader community. If you or your team are interested in presenting during the TRX webinar series, there will be a link to complete the request form at the end of our series today, or you can contact the America Makes TRX webinar series administrator, Jason Thomas, directly. A few important notes before we kick off the series. At the end of today's presentation, there will be an opportunity for a Q&A session. If during the presentation you have a question, please submit it in the Q&A space on your WebEx screen, and I'll ask it during the Q&A session. I will do my best to get all the questions answered. Today's webinar is on Synergistic AM, how ultrasonic additive manufacturing helps other AM processes. Without further ado, it is my pleasure to introduce Mark Norfolk. With over 20 years experience in manufacturing, research and development, and shop floor management, Mr. Norfolk leads Fabrasonic in the commercialization of ultrasonic additive manufacturing technology. Mr. Norfolk led EWI's development and research into UAM for 4 years leading up to the inception of Fabrasonic and has been with the company ever since. Prior to joining EWI, Mr. Norfolk held numerous manufacturing and management positions at Deere and Company in Moline, Illinois. Mr. Norfolk holds an MBA from the University of Iowa and a Bachelor of Science in Welding Engineering from the Ohio State University. Mark, I'll now turn it over to you and your team.
All right, well, thanks so much for the introduction. Having a little, hang on one second, I'm having a PowerPoint issue. All right, there we go. So agenda today, kind of at a high level, we'll talk a little bit about what UAM is. Many people haven't heard about our technology. We'll give you a couple examples of some capability and some examples. And then we want to talk about the interplay between different processes, because we see this as an area of growth. And, you know, one day we hope to see machine shops that not only have a lathe, a mill, and a drill press, but have a powder bed system, a binder jet system, and a UAM system, so that, you know, each additive technology can do, you know, those activities for which it is best suited. And I think in a future state, we're going to see those shops with multiple AM modalities, all under one roof. So a little bit about ultrasonic additive. We're a 3D printing process, but our major difference is instead of using powders or wires, we're using thin metal foils. And instead of melting those feedstocks, we're actually welding those feedstocks in the solid state at essentially room temperature. And the way we're doing that is with ultrasound, and I'll explain that later. But some of the differences that evolve from the fact that we're doing this at room temperature enable us to make parts that you just couldn't make with other manufacturing technologies. The first aspect that we do a lot of work in is printing multiple materials in the same structure. Whenever you melt metal, you take an aluminum, a copper, a titanium, like in the center picture there, and you melt those with an arc, with resistance, whatever. When you re-solidify that, you get a brittle intermetallic. And maybe that's what you're looking for, but 9 times out of 10, engineers are looking for something with a little ductility. With our process, since we're not melting, we're not actually mixing those two, and we avoid forming those brittle intermetallics. That means at any point during a print job, we can switch from one material to another, and typically they're all metallic. The picture on the right shows layers of aluminum and titanium, aluminum and copper, but we can get into more exotic materials like tantalum, tungsten, moly, Invar. All those different metals can be combined into a single print job. Now, you might be asking, why would you want to do that? And typically, we're trying to use the strengths and weaknesses of each material where they're needed. So for the aluminum and copper, we often use copper right where there's a heat source and a heat exchanger. but we don't want our whole heat exchanger made out of copper due to weight, so we'll mix in aluminum, and the combination of the two gives us an optimized performance. On the left-hand side, we're showing some tantalum and aluminum. That's actually a radiation shield. By stacking different layers of dissimilar metals, we can restrict or lower the amount of radiation coming into some of our structures. So we do a lot of work with electronics packages and shielding those, from certain radiation environments. Another capability that is derived from the solid state nature of our process is the ability to embed electronics. So because we're not melting the metal, at any point we can stop our process, come in, drop in a sensor, and then continue to print over top of that. In the center picture, we have a picture of a fiber optic cable embedded in aluminum. It turns out you can turn a fiber optic cable into pretty much any sensor you want, whether it be a strain gauge, a thermocouple, measuring vibrations, measuring accelerations. That can all be done with a fiber optic cable. So it's one of our favorites. On the left, we have embedded thermocouples, just a standard K-type in this case. We have many applications where customers want to know the health of their part while it's in service. By embedding these sensors in a specific location, we can get true health monitoring data off of a part continually in service. Other embedded electronics may be controls, data, and even some active elements for opening and closing valves. That type of thing can be embedded into a solid metal part. The last area we get into is not because of our solid state nature, but it's because our systems are hybrid. That is to say, we have both additive and subtractive in the same box. So we're basically taking our welding device and making it another tool in the tool changer of a CNC mill. Because of that, we can make internal shapes of any shape and size, but instead of those evolving from powder or evolving as we weld, all of those internal surfaces are going to be CNC milled. So that allows you a much tighter tolerance, a much better surface finish in interior portions of a three-dimensional part. Like I say, any 3D printing process can make internal geometry. It's kind of our differentiator, is that all of those surfaces are going to be touched by a mill. So you have a little bit more care and feeding on those surfaces. Another area that we're active in is embedding non-metallics into a metallic structure as we print. And those typically are for high strength applications where we're making something like a metal matrix composite. All three pictures here are aluminum parts that have been reinforced with ceramic fibers. So you can take a 300 KSI fiber, embed that in a 40 KSI aluminum, and have selective reinforcement is the term we use. We're strengthening material just where we need it to be. So this does not have to be a fully 3D printed part. We can print these materials, on the outside of a part in addition to an existing part, but allows, combining dissimilar materials in this case to achieve an engineering objective. The last thing that's a little different of our process is scale. There are a lot of other technologies that get to this scale, but not all of our metal systems get this large. We have the ability in our largest system to print 6 foot by 6 foot. Our printing deposition rate is typically in the 20 to 40 cubic inches an hour. Just as maybe a comparison, I think powder beds are usually in the 1 to 3 cubic inches an hour for a single laser head. So it's a little bit faster than some processes, but I would never call it fast. As mentioned, all of our systems start off life as a CNC mill, to which we add this welding technique. So this is just a short video that shows some aspects. Instead of having a fancy software to go along with our systems, we're actually using straight up CAD/CAM. So we're using off-the-shelf CAD/CAM packages to drive our mills using G-code. The only thing that we add is kind of a weld on and weld off G-code. So if you have experience with CNC milling, you probably already have a good understanding of how to run our machines. As mentioned, all of our machines do milling and additive. So what we'll do is we'll come into an existing part or maybe a base plate. We'll mill in some internal features, and then we'll start to print over those features. At any point during the print job, we can come back in with a mill and add more features as we grow into height. Our feedstocks, again, are all foils. Those foils tend to be in the 6 to 10 thousandths of an inch range. So about 150 microns is a normal layer height for us. And we can print different foils. So we can print aluminum for a while, then bring in copper for a while, then bring in titanium for a while to get those multiple metal structures. The one nice thing about having foils as a feedstock is price. Foils are openly available in the commercial market. Just to give you a sense of material cost, right now for 6061, we're paying about $6 a pound for our foils. So the feedstocks in the economics tend to kind of fall out of the economic model. Really, we're basing pricing mostly on machine time. But as you can see, everything is kind of a combination of both additive and subtractive in the same system. So a little bit about how we accomplish this. We have, again, a weld head. We also refer to that as a horn. It's an acoustically tuned device. On either side of that, we have piezoelectric ceramics, and we put a sinusoidal wave electrical signal into those transducers, and they vibrate the entire structure left to right on the order of about 30 to 40 microns. So that horn that you see in the left-hand picture, that's moving left to right 20,000 times a second at about 30, 40 microns. As it's vibrating, it's rolling forward out of the page. And as it's rolling over these foils and bonding those down to the surface. And then, of course, we can come in at any time with the CNC mill to affect geometry. So in effect, we're printing near net shape and then milling to get the exact shape that we're looking for. A little more on the bonding process. Ultrasonic welding has, again, been around since the 1960s. All we've done is taken this 1960s technique that was made for electronics and scaled that up with a lot more power. An ultrasonic wire bonder is in the 100-watt kind of range. Our systems are in the 10,000-watt kind of range, which allows us to weld these much wider strips. The general idea is metals like to stick to other metals. But down here on Earth, all of our metals are coated with an oxide or a rust. What ultrasonic welding attempts to do is bring those two surfaces together and grind the nascent surfaces back and forth. That vibration is actually scrubbing away the oxide layer on the surface of the metals. We scrub that oxide away. We have virgin metal on virgin metal, a little bit of pressure, and we get a solid state bond. It's similar or akin to an explosion bond or a friction weld in that it's a solid state happening at very low temperature. As we mentioned, dissimilar metals is a big area of work for us. This is a chart of many of the different metal combinations that have been tried with ultrasonic welding. We have tried most of these with our system. And typically, if that 1960s technology of ultrasonic welding works, it also works for our systems. The things that are harder for ultrasonics are things that have high lubricity. So something like a lead, which is somewhat self-lubricating, is not a great candidate. But most metals in general are. As far as difficulty, the higher the yield strength, the more difficult it is going to be to weld the material with this ultrasonic process. So that's always a consideration. Typically, the higher the yield strength, the thinner the layers in order to accommodate that disparity in strength. On the left-hand side in the bottom, we have a micrograph that shows kind of a unique combination. We have aluminum on the top, copper on the bottom, and silicon carbide fibers embedded into the matrix, so a true metal matrix composite. The one thing I would mention here is I would say that the aluminum is bonded to the copper, but I would say the silicon carbide is embedded in the aluminum. We're not actually bonding a metal to a non-metallic. Typically, we're going to embed those where we're squeezing metal around them so that we interlock mechanically, so that we can transfer strain from the matrix to the fiber, but I would never call it a true metallurgical bond. So we've looked at some of these pictures in another slide, just reinforcing the idea that dissimilar metals are a large part of what we do, mixing materials, doing things like cladding, in the center of a part, adding features with specific metals. We've printed materials that have a custom coefficient of thermal expansion, or materials that have a variation in CTE over the Z height as we print. So we change our layering structure as we go up so that we can have a variable CTE or a variable modulus through thickness. And that's all possible because we can weld these dissimilar materials. The picture on the left is a heat exchanger, which is a great example. Our number one combination is aluminum and copper. Again, copper is heavy, but it wicks heat away great. So mixing those is a good opportunity. The top right is a transition joint from aluminum to steel. Often those type of joints are made with explosion welding. By printing that, you can get a shape that's nearer to what you're trying to achieve and quite often reduce your price. And on top left is what I would consider more of a cladding. So not our traditional 3D printing, but using the welding technique to add an expensive metal A onto a cheap metal B. As we mentioned, the hybrid nature of the process does allow for things like heat exchangers. And actually our number one commercial product is building heat exchangers of all types. We've built parts that have pressures in excess of 6,000 psi, helium leak rates that are hard to measure. A lot of our helium leak tests we have to outsource because it's such a high hermeticity. And as you understand from other 3D printing processes, you have quite a bit of geometric freedom as to what the device can look like. Additionally, you can mix materials, and we do that often to enhance or optimize the structure. Channel sizes, in the bottom right, you see some channels that are about 10 thousandths of an inch. We've done channels up to several inches. As you get into larger and larger channels, we do need to use some support materials. So when we're welding over a large void, we are pressing down with a considerable force. If you don't have something in that cavity ready to push back, you can deform metal into the cavity. So larger structures like the picture shown here with Justin, we're going to use a water-soluble support material that is patent pending right now. But you can see, the applications range from something as small as 1 inch by 1 inch up to, heat exchangers that are maybe 5 foot long. Everything along that scale range is possible. We often can't share our projects due to confidentiality, but there's some that we are allowed to share. So we'll go through a few heat exchanger examples. The first one is a CubeSat. This was made for Utah State University in cooperation with NASA JPL. They were looking for both a radiator, that would be the black structure on the left, and a cryo cooler mount, which is the picture in the bottom right. And really how 3D printing helps this design is by optimizing the amount of material, by making internal channels exactly where they need to be. We're able to both simplify the assembly as well as increase the performance by getting materials exactly where they are needed. Both of these parts were 6061 aluminum, although we've done similar components out of 7075, 2024, 5052. Any of the aluminum alloys are certainly fair game. A second kind of case study was a part that was made for NASA JPL under a Phase 2 SBIR. This part was intended for the Mars rover. Unfortunately, we didn't quite get done in time, but it's a good educational case study. The part that flew, the part that's on Mars today, was built by taking an aluminum CNC milled plate and then epoxying on stainless steel tubing. So you can imagine the epoxy gives somewhat of a thermal break, as well as adding a considerable amount of weight, as all those tubes also were bolted with saddles. JPL was working with us on some other projects, and they asked us to take a look at this. In the process of about a month, we were able to just take their base design and turn it into a 3D printed structure. We didn't try to optimize anything. We just took their pipes and kind of turned that into a 3D printed part. But by making it monolithic, we were able to take 30% of the weight out. We got rid of all the epoxy, all the saddles, without any real redesign. And by getting rid of those thermal breaks, we were able to get significantly better performance. And this is not new to ultrasonic. This is the trend in additive. By simplifying parts, by taking multiple components and integrating them, multiple capabilities, and integrating them into a single part, you increase performance, reduce weight, reduce time and cost. So another topic we've been looking at is embedding electronics. I wanted to give a few examples of that. The first example is a fiber optic strain gauge. So as I mentioned before, you can take a fiber optic cable and pretty much turn it into any sensor you want if you have the right interrogator. In this case, we were making some parts for NASA Langley. It's a component that they've studied for about 20 years, and they really wanted to make sure that their models of this part matched the real world. So what we did is we printed the entire component, but we printed it with 6 fiber optic strain gauges. On each fiber, we actually had 6 locations where we could measure. So we basically embedded 36 sensors into this part, and we put it in a fatigue rig and studied not only kind of the steady state cyclic loading as you see here, but we actually ran it out to failure. And in the fiber optic strain gauges, you could actually watch the plastic zone of the cracks as they approached the fiber optic until the fiber optic eventually failed. So it was a really interesting way to study and correlate a digital twin of a part where you have actual data from inside the part. The pictures at the bottom right actually show the embedding. The picture at the far right is a coated fiber. So we took a ceramic fiber and it was coated in aluminum by a third party, and then we embedded that. And you can see that the matrix of the print job flowed around that fiber, fully encapsulating it. Like I said before, this would be fully embedded, and we can share strain or transfer strain from the matrix to the fiber. The picture on the left there is actually a plastic coated fiber. So many fiber optic cables on the market have a plastic coating on them. This plastic coating does deform quite a bit, but we saw similar performance in that by compressing that plastic, by flowing metal around it, we were able to transfer that strain again from the matrix to the fiber successfully. Another example also from NASA Langley was a bracket for a drone. As you can imagine, testing 3D printed parts on real flight hardware is not trivial, but testing hardware on a drone is pretty easy to do. So we printed a bracket and a strut from a drone, and we're able to collect true strain time histories of those components while they were functioning. And this gets to the idea of health monitoring. If you can get true strain data from your parts in service, you can better extrapolate life, inspections, and the overall health of the system. So this is an area of active interest for us commercially. And kind of the segue into multiple processes is multiple functions. With ultrasonic additive, we have this capability to mix materials, to add electronics, and that is allowing our customers to design parts with multiple functions. So instead of having a heat exchanger that's bolted up to an electronics package, that's bolted up to our structure, that's all surrounded by a radiation shielding package, we can now take all of those functions and put them into a single print job. So as we print, we're printing in our integrated cooling, we're dropping in our electronics packages and then surrounding those with heavy metals like tungsten, titanium, tantalum to stop the radiation. And as we're printing, we're also printing in reinforcement with other materials like ceramics so that we get the high performance that we're looking out of these components. And that's really a drive that we see in industry, is really not just trying to simplify parts, but simplify capabilities and simplify capabilities into one part. And that's really what's led us into starting to look at combining multiple processes together to meet our customers' needs. So I want to talk a little bit about how ultrasonic additive and how Fabrasonic are working with other 3D printing processes, to further the needs of our customers. The general pain point in AM that I don't think is a secret to anyone working in the space is we have this competition between feature size and resolution. If we have a process that gets really, really fine resolution, that typically has a fairly meager build rate. However, if we have an additive process that has a really great throughput, really high deposition rate, we tend to have to sacrifice our feature size. They tend to be much larger beads, much larger prints, so that we lose that resolution. So in the bottom left, I think I stole that off of Velocys's website, or I'm sorry, Velo 3D. I think I stole that out off their site, but it's a powder bed printed thermal management device. And at the right, we have a heat exchanger that Fabrasonic printed. That's about 5 foot long. And in additive, we typically have this either or, and we really want to look at how can we combine those processes to get the best of both worlds. So what we're really talking about here is synergy, taking 2 or more things and putting them together to get a combined effect greater than the sum of their separate existences. So in our world, we do a lot of work with copper and aluminum. We want the lightweight of aluminum, but we want the high conductivity of copper. But why can't we do this with metal AM processes? Now, a lot of the work that we do, we're not allowed to talk about. So in this case, I'm just going to give you a concept. But what if we had some thermal structure that we're working on? Let's say it's 6 foot long. It's a very large thermal structure. But in most cases, when we have these thermal structures, there's discrete regions where heat is being pulled out, right where we have an electronics chip, right where we have a process. So what I would propose is maybe we could print, very fine featured thermal cavities, if you will, out of, say, powder bed fusion. And we print those so that we have a very, very high rate of heat rejection from our part. But we need to integrate that into a much larger part. So then we can take something like ultrasonic additive, where we can mill in connection channels, fluid passages between each of these discrete locations where we've printed this super optimized organic shape to pull out heat. And then we use the larger process, ultrasonic, to connect all those dots and seal in that powder bed component into the much larger heat exchanger. And this is just a concept. We'd love to try this out, and we probably will someday. But it gives you an idea of how 2 AM processes that are at totally separate ends of the scale and really don't compete can be used together to get a much better product. Again, down the road, I think 20 years from now, you're going to see a shop that has a powder bed machine, a UAM machine, a DED machine, all in the same shop, and we're trying to head down that path. Another more concrete example that I can share at a high level, this component right here was a component we printed for a customer. The specific application really needed some organic shapes. So you can see the bottom of this part has some organic structure printed on a powder bed system. In this case, it was printed out of stainless steel. But the same component needed some electrical sensors embedded into the structure. And we also wanted to see some dissimilar metals for how the part was going to be used in service. So what we did here is we combined powder bed and UAM to make the part that the customer needed. So first we went into a powder bed system and printed the organic shape out of stainless steel. Then we brought that part over to an ultrasonic machine where we used the CNC capability to mill in a cavity. We installed some electronics packages, and then we printed aluminum over that electronics package to seal it in and allow us to have that dissimilar metal connection that was required, further down the manufacturing line. But this gives you a great example of bringing together two technologies to get the product that the end customer is looking for. And I think this is a trend that we're going to see more and more of. We have some other examples that we can't share, but certainly there's a lot of opportunity to use a hammer, use a screwdriver, use a file, all together to get where we're trying to go. Another example of this, I didn't want to make this all ultrasonic based. This is an example that Paul Gradle at NASA passed on to me. This part is part of a rocket, and they used powder bed fusion, printing copper, a type of copper called GR cop, developed, I think, at NASA Glenn, to print a structure with embedded channels. So they're flowing fluid through these channels. But they needed a larger nozzle at the end of this than what was possible in their powder bed system. So they transitioned that to a DED system, a laser-based powder system, to print out the rest of the nozzle. So this is just another example of how we can take different tools in our toolbox to get to the end product that we're looking for. One note of caution here, if you're using fusion-based processes to mix dissimilar metals, you got to think that through. It's certainly possible, but the metallurgy is something you just want to put some thought into before you run off and do it. But just another example, how can we combine these different processes that really are good at different things and bring them together to get an application that we're looking for our customers? So going maybe even a little bit on a different tact, one other activity that we've been involved in is actually helping understand better a powder bed fusion system. Fabrasonic is a spin out of a nonprofit, Edison Welding Institute. They have all kinds of additive toys. And one day we were having lunch with one of our colleagues who's a powder bed guy, and he was lamenting the fact that they were having some distortion issues, that they had a build that they got halfway through and there was a build failure, and they didn't know about it until they were completely done. It's like, man, I really wish I could, look into that powder bed and understand what's going on as I'm printing. And I said, well, hey, we're embedding sensors in metal plates. Maybe we could embed your build plate with strain or temperature sensors so that you could really understand what's going on. And that led to a project with the DLA. We're actually in a phase 2 of that program, and we call it the Smart Baseplate. Let's use our solid state printing technology to embed sensors so that we can help out the broader community, working on other techniques, like DED, powder bed. The sky's kind of the limit there. This picture right here at the top is a build that was made on a powder bed system. And at the bottom, you see a color map there. The light blue line is where our fiber optic strain gauge was embedded. So anywhere along that line, I can tell you within about a millimeter the actual strain on that fiber optic cable. Much like you would do with strain gauges, you can do some math if they're oriented at different locations and actually resolve both magnitude and direction of strain in the build plate. So at about 100 to 200 hertz, we were collecting strain in the build plate as we were printing on it with the laser powder bed. And what this gives us is not only kind of a detection method so that we can kind of quantify if something's going wrong in the build, but we can really understand how the residual stresses are building up. And we've had several customers get involved with this, and oftentimes what they really want this for is to calibrate their models. we all have models of our processes, and often those models have these cheater factors that we throw in to try and make it more and more like the real world. Well, if we can provide data, actual strain time histories, as a part is evolving, we can use those to calibrate our models and get our models better and better. Long term, we think there might be some applications in production such that you can compare kind of every build to some known good baseline. And really the idea is, can we identify flaws sooner in the build and stop builds that may have a problem? But as a research tool, it's fantastic, and we hope someday it's also equally beneficial in a QA kind of standpoint. I'm going to try and run a video here that shows the evolution of strain throughout the build process. We'll see if it transmits well. So this is a kind of a homebrew powder bed system at EWI. They kind of built it themselves so that they could change things and put in sensors like ours without having to worry about voiding some warranty. So it's a little bit different than your traditional commercial systems, but it's the same idea. We're spreading powder and then melting those with a laser. And here we are actually welding, and you'll note that those kind of blue waves that follow, that's actually strain in the build plate being created by melting and resolidifying of the powder. So we're actually watching, the strain evolve in the part, over time. Now this is sped up 30x. If you didn't know that, note that. But you can actually see, the strain as each pass of the laser goes back and forth. And then we had several features here that, obviously are not designed for a good powder bed outcome. Some of the sharp shapes were there on purpose so we could see if we could detect, delamination, a separation, a part peeling up. And what we found out is we could actually, see a delamination or a build plate failure quite early and track that as it delaminated. And we never hit the recoater blade. So we were able to, continue to see our defect and how it evolved before we ever would have seen it from the outside. So it's just an interesting tool. And again, it's all about how can we leverage these additive processes to help one another. And this is just another cool application. So in summary, we've talked a little bit about ultrasonic additive. Again, solid state process, hybrid at room temperature, allows us to do some cool things. Print dissimilar metals, embed electronics, and make those complex internal shapes with CNC surface finish. How can we leverage our additive technologies to help one another? Obviously, we talked about the smart build plate and how we're trying to help our powder bed brethren in the same building understand their process. But really, I think the goal at Fabrasonic and with some of our partners is really to use each additive process for what it's good for. Let's combine those processes, and maybe we add, water jet, maybe we add CNC milling to get to the end product we're looking at. Not every part has to be 100% 3D printed by one technology. So with that, I think we have some time for some questions. I'll open it up to what you want to talk about.
All right, thank you, Mark. Yeah, we'll now head into the Q&A session. That was a great presentation, very interesting process. And once again, for our attendees, if you do have any questions for our presenter and you haven't done so already, please go ahead and type it into the Q&A box. I do have some questions here. So our first question for Mark is, can you deposit silver via USAM on a copper part? We're trying to use that to optimize heat transfer.
So we haven't tried that specific combination. We've done silver to aluminum. So I'm fairly confident it would work, but we've never actually tried it. Would love to talk to you a little bit offline on your application. But yeah, I think that's probably doable. We just haven't proven it yet.
All right, thanks, Mark. So another question here. So looking back at the smart base plate, how many times can one of those be reused?
Yeah, that's a great question. You know, folks in a production environment are going to want to, you know, cut off their part and put it back in service. What we're looking at is how deep we can bury the sensors without losing the sensitivity. So it's kind of a spectrum, right? If we bury the fiber optics, you know, just below the surface, we get high fidelity of data, but then we can only cut one or two parts off before we've, you know, cut into the sensors. Alternatively, we could bury the sensors a quarter-inch down, which would, you know, allow you many parts to be built off that same base plate, but you know, perhaps we lose some fidelity. So in that phase 2 STTR we're working on, or SBIR, excuse me, what we're looking at is perhaps can we print a part, cut it off, and then send it back to have UAM add more material to it so that we can reuse those plates more and more often. So I think we're not sure yet, but we're looking at how can we get as many you know, powder bed runs off of a single instrumented plate as we can to keep the cost down. Great question.
All right. And then following up on that question, how accurate is that smart base plate?
Yeah, that's something we're also experimenting with. Along the length of the fiber, we're able to get measurements about every millimeter. And that's using the existing equipment that we have. And we're running about, I think, 100 hertz, something in that range. And really the resolution that you can get inside of your 3D printed part depends on how closely we pack that fiber in on itself. So if we take that fiber and we, you know, use, say it's a 2-meter fiber, and we use all 2 meters of that in a very small space, we can get just excellent resolution on our strain. However, you know, you may not be interested in just one location. We could take that same 2-meter fiber and spread it out over the whole, you know, 10 by 10 or 12 inch by 12 inch plate, which kind of reduces your resolution but gives you a broader picture of the build. So that's something that's adjustable based on kind of customer requirements, and we've kind of gone both locations, but you know, our minimum right now between measurement points is about 1 millimeter.
All right, thank you. So let's see, got another one coming here. So we saw the video where you were laying down the foil. So what is the maximum width of foil you could put down? So say you were building like a 1-inch tall part that's 4 by 4 inches cubed. How long would that deposition take?
Surely. So there's a couple different modes that we can run in. If we're making parts that have high variability but low volume, we typically run 1-inch wide foil. It's a standard width that we can, you know, make tool paths for automagically and just run. So if you know it's high variability, low volume, we're going to use 1-inch wide foils, and we'll stack those side by side and overlap them so that we get good tie-in from foil 1 to foil 2 to foil 3 to foil 4. However, if we're doing something that's more of a high volume run, we may lay down 4-inch wide foil and just make 4 welds. In some of our machines, we have multiple weld heads so that we can, you know, make 4 welds, or in one case, we have 10 weld heads all together in the same system to get that throughput up. So it's kind of a question of, you know, the machine. Our base machines are running around that 20 cubic inches an hour in aluminums. But as I mentioned, we've made some custom machines with, you know, 10 weld heads to really get that productivity up. And it really is a multiplication. You know, if you have one weld head is 20 cubic inches an hour, you know, 10 is 200. So it's kind of a linear. The more heads we can stick in the process, the faster we can go.
Okay, and then and is it the same for all materials, or do some materials print faster than others?
Yeah, it's really dependent on yield strength. So the higher the yield strength, the slower that we're going to print. So you know, when I'm quoting, you know, 40 cubic inches an hour on one of the slides, that's in an aluminum alloy that's fairly low strength. So we can go pretty quick. If we were talking stainless steel, we would be more on the bottom end of our scale. But the higher the yield strength, the slower we're going to have to go.
All right, thanks, Mark. So let's see here. So we've got a lot of projects here at America Makes, and I know a lot of people are looking into things like hipping and heat treating. What sort of post-processing does UAM need normally?
Yeah, that's one of the benefits of a solid state process is because we're not getting hot, because we're not melting anything, we're not really making any changes to the microstructure, to the precipitates in the microstructure. So the material properties we have coming in are pretty much the material properties we have going out. The exception to that is in the Z direction. I mentioned that we're scrubbing back and forth to try and clean off the oxide. Well, we're doing this in an open air environment, no shielding gases, no vacuums, which keeps our costs low, but we do include some oxide in the bond line. So that limits our strength in Z. We typically see maybe a 20% hit in Z. So from a grain structure standpoint, we really don't have much use for heat treating. We're not doing much in post-processing to deal with microstructure. However, if we want to try and get rid of that oxide layer, we can do things like HIP or even some straight up traditional heat treatments. And that's very alloy specific. So if it's a precipitation hardened aluminum, if you HIP it, you wipe out the properties and basically anneal it. So you have to have maybe a different heat treat designed for that. But if it's something that is just a grain size, grain structure thing, you could maybe just straight up anneal it, and that would help dissolve those oxides back into the matrix. But I'd say 90% of the parts, maybe 95% of the parts that we build, we don't do any post-processing on. Our customers understand that we have a debit in Z, so we design the part such that the orientation of the principal stress direction is not in Z, or they understand what the limits are. So I'd say for vast majority of parts, we do no post-processing. And again, since we're CNC milling as we go, it kind of comes out of the machine ready to go. So we do save a lot on the post-processing side.
All right, great. Thanks, Mark. All right, so you mentioned powder bed quite a few times during the presentation. Do you think that UAM and powder bed will ever be done on the same machine?
That's a great question. The two processes live in very different worlds. Powder bed, you do need a special environment that you need to contain, and you need to manage the powders. So I doubt we would ever have them in the same machine, but I can definitely see customers that are already thinking about putting the two machines in the same room 2 feet away. So that as soon as you're done cleaning out your powder out of your powder bed part, you drop it into a larger assembly in a more complicated part that's being sealed up by UAM.
All right. So let's see. I think we have one more here. So you mentioned a lot of different metal alloys that work with UAM. Can you do 7075 T6?
Yes.
All right, great, short and sweet. All right, so I just want to thank everybody for joining us today. That will wrap up today's TRX webinar series. I would like to once again thank Mark for the great presentation. If you have further questions for Mark, please reach out to him directly at the email that we have here on the screen, mnorfolk@fabrasonic.com. This presentation will be available on the America Makes YouTube channel as well if you'd like to view it again. There will be a post-webinar survey going out to all of those who participated today. We do really appreciate the time that you take to provide America Makes feedback so we may continue to improve and strengthen that community. And as a reminder, if you think that you or your organization will be interested in sharing on the TRX webinar series, please fill out the form that follows the presentation or reach out to myself, Jason Thomas, at jason.thomas@ncdmm.org. Thanks again, Mark. Everybody have a great day.